Hi, my name is Benjamin Alt. I'm a research scientist at ArtiMinds Robotics and a PhD student at the University of Bremen. And today I would like to present to you our latest paper, Robot Program Parameter Inference via Differentiable Shadow Program Inversion. When you program an industrial robot today, you typically do so by combining movement primitives or more complex action primitives like grasp, force-controlled search, or insertion into complex program hierarchies. So this is a skill-based but still a fundamentally manual programming approach. That's very prevalent in the industry. This way, one can generate relatively complex robot programs, which can be very performant, very fast, as you can see here, and very reliable. So the advantages of this approach are that you reach very high precision and performance in your robot programs. They can be edited by hand by humans, and they can be certified because their exact behavior is well known. But this kind of programming is still a manual process and requires a considerable amount of expert knowledge. In service robotics, on the other hand, there's been a kind of ongoing trend of doing more or less autonomous robot self-learning, as seen in this video, where a robot learns new tasks essentially from scratch. So you don't use predefined skills and parametrize them and combine them manually, but you have the robot learn new skills from scratch, and then maybe combine these fully learned skills, but the learning is much more autonomous, and we can call this self-learning. This is a very intuitive way of teaching robots to solve tasks, and it allows for very flexible perception action loops, and the robot can adapt to unknown environments. However, this is a very data-intensive process, so you might need a lot of iterations to get the robot to do exactly what it is expected to do. And the learning process and the results are hard to predict or to understand for humans. The programs are very hard to edit by hand, which is very important for industrial robotics, where you might want to tweak your assembly line later on. And they're also hard to certify. So coming back to the skill-based robot programming paradigm. Here we have a skill-based robot program on the left, where the robot first performs a contact motion onto the PCB, then does a spiral search, and then in the end opens its gripper to deposit the workpiece. So this program has a set of parameters, right? Particularly, for example, the spiral search has its extents, so how large the spiral is, maybe also an orientation of the spiral, the forces, how hard the robot has to press onto the surface, the velocity and the acceleration of the spiral, etc. So the success of the skill really depends on these parameters. So what we want is we want to find the optimal parameters such that our spiral becomes as reliable as possible, or maybe takes as little time as possible, or a combination of them. So how can we infer these parameters automatically in a data-driven way? Our idea is to leverage differentiable programming here. That concept's been around for a very long time. Here, for example, we have a differentiable computation graph where C is W2 times A, and D is W4 times C plus W3 times B, and so on. And L is a function of this graph. And of course, this is differentiable, so you can compute the gradients and backpropagate them and optimize A. So when you train a neural network, you would optimize the weights W, but we're really interested in optimizing the inputs of this program. And we would like to apply this concept of differentiable programming to industrial robot programs. So here's the general idea of this paper. First, you want to find a differentiable representation of a set of existing robot skills, such as, for example, spiral search. And we can't just program these skills by hand in a differentiable way. We need some form of learnable component because action in the real world are non-deterministic in a way, because the environment may be different every time. So whether the spiral finds a hole doesn't only depend on the implementation of the spiral, but also on the environment. And then we want to be able to combine these differentiable skills to more complex differentiable robot programs, and we want to leverage gradient descent to optimize the parameters of them. So this is our proposed method, shadow program inversion. We start with a regular robot program composed of skills. This can be any type of skills. We applied SPI to DMPs, for example. They can be functions in your favorite robot programming language. So any kind of robot skills that have parameters. And we want to find what we call the shadow program, which is a differentiable analog, which basically is a graph of graphs. So a differentiable graph of differentiable skills, which is a model of our original program. Each differentiable skill is essentially a neural network, which takes the skill input parameters as inputs and predicts an expected trajectory, so the TCP pose and range over time. They are predictive models of our original skills in a way. And we train them by unsupervised learning, where we simply execute the original robot program over and over and over again, sample some trajectories, and save the parameters that we used. And then we use this to learn predictive models for each of those skills in an unsupervised way. And then once we have our trained differentiable shadow program, we can perform something called neural network iterative inversion, where we freeze the weights of our networks and simply do gradient descent in the input space, with respect to a loss function which comes from our task objectives. So for instance, if we want to minimize the cycle time, well, then we just penalize long trajectories. So we do gradient descent such that in the end our inputs are so that our neural networks predict short trajectories. And this gives us the optimal skill parameters for our task objectives, which we can then feed back into a robot program. And if we want to, we can run this in a loop and keep making our program better. So this is a zoomed in view into a differentiable model of a spiral search. So you see on top it has the exact same parameters as the original spiral search. And during the forward pass, what we do is we first bootstrap kind of an ideal spiral from a differentiable Cartesian motion planner. In this case, this is just an Archimedean spiral with a velocity profile on top. We use this as an algorithmic prior to make the learning problem much easier. We then feed this through a recurrent neural network, in our case a 4-layer stacked GRU, to predict a kind of residual trajectory, so the difference to this ideal spiral. And then we apply this residual to get the real expected trajectory y hat, which is the trajectory we really expect when we execute this in our environment. So once we trained differentiable models of each skill via unsupervised learning, we can then construct an equivalent shadow program to our original robot program. So here our shadow program is in gray, and it's just the learned models for each of the skills in our original program. We connect them by propagating the robot state. In this case, Sout, the Sout output, to the Sin input of the next skill. We then combine these trajectories to the full expected trajectory, which we can then score with our task-dependent goal function, for instance, cycle time. And then we compute the gradients, backpropagate, and adapt the inputs of each skill. Shadow program inversion has several really nice properties. So for once, it's asymptotically optimal. So the convergence properties of the Adam optimizer also apply here, which means that we can asymptotically guarantee that we find the globally optimal inputs for a robot program given our task objectives. Also, it separates the learning of the skills from the inference of the optimal parameters of the skills, which means that we can learn the skills in advance, build up a library of learned skills, and then we can combine them to a robot program afterwards without having to retrain them. And we can run parameter inference with respect to several different, and this is zero-shot generalization, loss functions without having to retrain. And this is really useful in industry, where, for example, you have several assembly lines all doing the same task. You only need to train these skills once, and then you can use them on every single one of your assembly lines and infer the optimal parameters there without having to retrain your models all the time. Also, our approach is a wrapper approach, which means that it's completely skill agnostic. You can apply this to any skill framework you want. We performed several experiments to demonstrate the validity of our approach in the real world. So first, we optimized the parameters of spiral searches to optimize several different goal functions. And in this case, we just autonomously collected a bunch of spiral searches, about 5,000 of them, and trained a spiral search skill. We also had a linear approach motion beforehand, which we didn't have to train because linear motions are deterministic, and we could just use our differentiable motion planner for this. We then ran our optimizer on the entire program, and as you can see, the parameters of the spiral, as well as the goal position of the approach motion, are optimized such that we optimally fit the distribution of the whole. And this is great because this way we can really maximize things like robustness. So in this case, the search would find the hole every single time because the entire distribution is covered by the spiral. We also compare optimization for different goal functions. So without retraining, we can optimize program parameters for, say, minimization of failure rate, as seen on top, where it creates a large spiral, or for path length, as seen here on the bottom, where the spiral becomes very small and fast. In another experiment, we optimized the parameters of contact motions to make contact, in this case with a PCB, with a set amount of force. And because we only require unsupervised learning, data collection and model training happen completely autonomously. So as you see here, after optimization, when the goal force is set to 5 newtons, we actually hit the PCB with exactly 5 newtons. And later, if we want to hit the PCB with, say, like 6 newtons, we can just rerun optimization without doing training again. And we can actually hit the PCB with exactly 6 newtons. If we were to do this as a human, this is very hard to tweak. So you would actually need to tweak the acceleration and velocity of your contact motion to produce this exact amount of newtons. In this case, it took no tweaking at all because we simply had to run inference again. We also did this for several other skill implementations, such as DMPs or UR script in this case, and on several surfaces with different spring characteristics. It turns out that our model was capable of learning the damping spring characteristics of these surfaces really well, and was completely agnostic with respect to the actual implementation of the skill, so it worked just the same for UR script functions, DMPs, or our own skill implementation. Lastly, we did an experiment where we inferred parameters for an entire pick-and-place program from human demonstrations in VR. So this was a collaboration with the Institute for Artificial Intelligence at the University of Bremen. We used their VR-based motion capture and motion tracking system, as well as their system to automatically annotate these motions and segment them to basically create loss functions from these demonstrations. We ran parameter inference so that the trajectory resulting from executing our motions was as similar as possible to these virtual reality demonstrations of the human. As you can see, we infer a set of program parameters which solve these tasks very quickly, reliably, and efficiently. To conclude, shadow program inversion combines the reliability and performance of industrial robot programs with the learning capabilities of neural networks. It's a wrapper method that's applicable to most skill implementations because it leverages an auxiliary learned model, which is differentiable, as well as a differentiable programming paradigm to then infer the optimal input parameters. It also zero-shot generalizes across task objectives, which makes it highly versatile for real-world industrial applications. In the future, we want to improve SPI's data efficiency by using meta-learning or transfer learning techniques. We also want to apply it to non-stationary environments, where the distributions of things in the environment change over time. We also want to integrate it with ongoing work on reinforcement learning for learning the structure of robot programs. And we want to seek further applications outside of industrial robotics, such as in the service domains. Well, that's it for now. Thank you very much for your attention. You can find our paper on arXiv. There's a blog post about it, and we published our code on GitHub. Thank you very much.